Okay, hi guys. So in this lecture, we'll be seeing more on Clausius inequality. So let's get started. So first of all, let me write that Clausius actually assumed whole of the universe as the entire system. So Clausius assumed entire system as a universe, or rather, Clausius assumed universe as an entire system. Simply as a system. Okay. Now we can write that universe is system plus surroundings. Okay, and ds total can be written as ds of system plus ds of surrounding. Okay, and we can write that ds total would be greater than equals to 0. So if delta S system plus delta S surrounding is less than 0, then it's an impossible process. Then it's a impossible process. Okay, and if it's equals to 0, then this is a reversible process. And if delta S system plus delta S surrounding is greater than 0, then it's a irreversible process. Okay, and ds of system is always equals to 0 for this irreversible process. Okay, so on a general basis we can write that ds of system would be greater than equals to 0. It would be 0 in case of reversible process, and it would be greater than 0 for an irreversible process. Okay, now let's see another concept, which is the calculation of entropy change. Okay, so in case of general heating or cooling, of solids, liquids or gas, we can write that dq is equals to mc dt. C is the heat capacity or specific heat capacity, and this can also be written as CDT, where C is the heat capacity simply. Okay. And ds, as we know, can be written as again dq by t, an integral of same. So we have the integral sign on both the sides of the equation. So for calculating the entropy per unit mole, we can write this as Cm, which is molar heat capacity, dt upon T, where DSM would be, rather SM would be having unit joule per mole Kelvin. Okay. Okay, so from this we can write that for n moles of a substance, we can write that ds would be equals to NCM dt upon T. Okay, so at constant pressure, we can write that ds would be equals to n cpm dt upon T, and at constant volume, we can write that ds would be equals to n cvm dt upon T. Okay, and this ds or s is in joule per Kelvin. And for solid, liquids, or gases, we have assumed that cpm would be equals to cvm, which would be equals to cvm. Cm would be equals to cpm, which would be equals to cvm. Okay, so continuing after this, that if cvm or cpm of substance is temperature independent from T1 to T2, independent from T1 to T2, then we can write that if at constant pressure, we know that ds would be equals to n cpm dt upon T, so we can write that delta S would be equals to n cpm ln T2 upon T1, just integrating the both the sides. And similarly at constant volume, we can write that delta S would be equals to n cvm ln T2 upon T1. Next point is, if the cpm or cvm is temperature dependent from T1 to T2, then let's say what happens if cpm is temperature dependent from T1 to T2, then we can write that cpm can be equals to a plus bt plus ct square So the value of ds would be n cpm dt upon t. So it would turn out to be, on integrating both the sides, delta s would be equals to n a ln, this is from t1 to t2, t2 upon t1 plus b t2 minus t1 plus c by 2 t2 square minus t1 square, and same can be written for CVM also at constant volume. This was at constant pressure. Same can be written for constant volume, or same can be derived in from at constant volume also. So with this we come to the end of this lecture. In the next lecture we will be seeing more on calculation of entropy change. So till then, good luck and goodbye.